So let us move to example number 6. Example number 6. You are told to evaluate the integral sine squared x dx, isn't it? Now to evaluate the integral, you can see sine x squared dx, sine is squared, and you cannot integrate any function which is squared, isn't it? Yes. You get rid of the power. So you see sine squared x is the same as sine x, which has been squared dx. It's easier. You don't need to go the whole of that process I was just explaining. It's easier because you can as well use, there are a lot of things to be used. You can as well use the concept of the double angle in trigonometry, isn't it? Isn't it? The concept of the double angle, if you have cos x plus x, see that is cos squared x minus sine squared, isn't it? Then if you key in the Pythagorean identity in cos squared x, what do you get? You get 1 minus sine squared x is the same as cos squared x, isn't it? Then minus sine squared x, isn't it? Then this side is cos x plus x is cos 2. Are you seeing that? So what do you get? 1 minus 2 sine squared x. Then what do? You make sine squared x the subject of the formula, isn't it? So if you make sine squared x the subject of the formula, you get sine squared x is what? Is a half. You bring it here. You get 2 sine squared x, then you remain here with 1 divided by that, is a half minus a half cos 2x. You know all that process of making something the subject of the formula, isn't it? So you think this is the first case of getting rid of this power to be in terms of multiple angles. So you think you don't have power, meaning you can now integrate this. Are we together? So when the power is 2, the best methodology to use is not De Moivre's theorem when the power is 2, when it is raised to power 2. You don't go to De Moivre's theorem. So it means De Moivre's theorem, I will be expecting you to go to De Moivre's theorem when you have power 3 and above. Are you seeing? Yes. Because power 2 is easier to use trigonometry. Is that okay? Yes. Instead of using De Moivre's theorem. De Moivre's theorem will give you the same answer, isn't it? But it will be a long process with just a power of 2. With just a power of 2, you just go to trigonometry direct, isn't it? Are we together there? Yes. Good. So it means where you have sine squared x, you are going to put a half minus a half cos 2x. Good. So in the hand, what do we now have? We now have, for you to integrate this, you are now going to have a half is a common factor, isn't it? Then you have 1 minus cos 2x dx, because we've expanded this sine squared x, we found it is a half minus a half cos 2x. So you see a half is a common factor. If you factor this out, you get 1 minus cos 2x. So you see a constant can be factorized outside the integral, isn't it? Then inside we remain with 1 minus cos 2x. So you see, you are now integrating everything independently, isn't it? Because this means, if you open this bracket, this means you have a half integral of 1 dx minus a half integral of cos 2x dx, because this one is independent with this, isn't it? Are we together? Yes. So if you integrate 1, what is 1? 1 is the same as x raised to power 0. So this is a polynomial, isn't it? You add 1 to the power and you divide with the resultant power. So in the first case here we have a half x raised to power 1 over 1, isn't it? The second here case here we have minus half. If you integrate cos 2x, that is, you use standard integration alongside algebraic substitution, isn't it? Because if you say let 2x to be t, meaning you are integrating cos t. Sendio, remember when you are differentiating cos, you are getting negative sign, isn't it? So it means when you are integrating cos, you are getting positive sign. Are you seeing the scenario? You pick it from differentiation, then you see the opposite, isn't it? So there you now have, if you integrate cos t, you get sin t. So sin t is the same as our t is 2x. Then at the end you divide by the derivative of the inner function, isn't it? Which must be a constant. Are you seeing the scenario? Then we don't have limits of integration, meaning at the end you have arbitrary integration constant, isn't it? So what do we have here? Now you simply simplify. If you simplify this first case, you have a half x, isn't it? Then a half divided by 2, you have 1 over, isn't it? 1 over 4 sine 2x plus c. Are you seeing that? Then that is the end of the integration process. So if you are given the limits, you simply remove C and you put the limits and you substitute the upper limit minus the lower limit in case of a definite integral.